Well, we've examined a thermodynamic variable, which is the internal energy of the system, U, and now we turn to the concept of enthalpy. Enthalpy, that's an interesting word. And let's look at what we've learned about the change in internal energy of the system, which is equal to Q under constant volume. That's exactly what the bomb calorimeter provided for us. And this bomb calorimeter set the entire foundation for measuring energy from a chemical reaction, because when we locked down the volume so that we only released heat in that chemical reaction, we could make those measurements extremely accurately. But what about constant pressure? When we think about chemical reactions, constant pressure is what dominates 90+% of all chemical reactions. Our body is a process where, as we look at it as biology, it's actually an orchestration of many, many chemical reactions, but they're all taking place at constant pressure. And anytime we burn natural gas, for example, or coal or whatever, that chemical reaction is taking place at constant pressure. So we create a new variable, enthalpy, and we define enthalpy as the heat release at constant pressure as opposed to the heat release at constant volume. So let's see what that means. Again, we always write down the first law, delta U is equal to Q plus W. But now we know that at constant pressure, this is Q at constant pressure minus the work term, P times delta V. All right, so if we introduce this new thermodynamic variable, enthalpy, enthalpy is defined as the internal energy of the system plus another term. And that other term is the pressure times the volume. All right, well, why is that term pressure times the volume sitting in there? Well, let's take a look. Let's take delta H, because we're going to always be interested in enthalpy release or the uptake of energy in a chemical reaction at constant pressure. So we want to calculate delta H. So delta H then, by direct inference, is delta U plus the change in the product of pressure times volume. But now let's suppose we take a condition for constant pressure. When we do that, we can write delta H as delta U plus constant pressure times delta V. All right, but we know what delta U is, so let's substitute that into the equation for delta U. Delta U is equal to Q released under constant pressure minus P delta V, but then we have the plus P delta V term from the definition of delta H at constant pressure, and lo and behold, that gives us the heat release at constant pressure. So that means that delta H, the change in enthalpy, is simply the heat release at constant pressure. So we have that relationship between delta H, and we have this relationship for delta U, which is to say delta U is equal to the heat release at constant volume. And we just remind ourselves that this is delta H of the system. And that defines a new thermodynamic variable, enthalpy. And it turns out for analyzing energy release from chemical reactions, it's enthalpy we focus on, because virtually all chemical reactions take place at constant pressure. So the next question is, why do we focus on enthalpy? Why do we care so much about enthalpy? And a hint of that we just discussed, and that is that almost all chemical reactions occur at constant pressure. So let's consider one of the most important reactions in all of the atmospheric structure that we live within, and that's the reaction between methane, which is natural gas, and the OH radical. And we're going to indicate the OH radical with a little dot at the top representing the fact that in its valence shell, there's one unpaired electron, and that one unpaired electron contributes remarkably to the reactivity of hydroxyl radicals with any other molecule. So we've got natural gas reacting with the hydroxyl radical, forming the methyl radical and water. So the question is, what does the reaction look like? Does it release heat or does it take up heat? And if it releases heat, it means that the change in enthalpy for the reaction is less than 0. And that strikes you as a little bit peculiar because it's producing heat, and yet delta H for the reaction is less than 0. And that convention comes exactly from the convention that says if heat is leaving the system, it's negative. And so all chemical reactions that produce energy have a delta H for its reaction that's negative. That means that this amount of energy is released when that reaction takes place. So the first thing we want to look at when we're analyzing any chemical reaction is, does it release energy or does it take up energy? That is, before we knew the answer to this, we could say, well, maybe when I react methane with the hydroxyl radical, maybe that reaction produces the methyl radical and water, but it requires energy in order to execute that chemical reaction. That is to say, delta H would be greater than 0 because heat has to flow into that system in order to initiate that reaction. Well, it turns out that when we do this calculation, it turns out that delta H is indeed less than 0, so that reaction gives off energy. But we don't know that until we've calculated the enthalpy. So let's do that.